I was going to talk about the early history of quantum information science when it was not anybody's day job to do it. And this is a picture from what I consider one of the formative conferences. It took place in 1981 at MIT, and it had about 40 or 50 people, including some Nobel laureate, or I guess just one Nobel laureate, Feynman, but a number of other people of similar stature, and at least one extremely peculiar person, who's right here. You can see here he is. He's Fred Cantor, and he would explain to us that he had a peculiar form of dyslexia that required him to speak very softly and very slowly, and he would sometimes forget his name, but he took care of that because you see it's printed on his shirt upside down so he can look like that. Anyway, he was one of the people there, and this was quite a day. So I'm going to talk about the very earliest history of the field, and I'm also going to try to talk about it in a way that if you are not, I guess you were one of the people who didn't hold up your hands, because it's important in this field for people to understand it, not in a way to practice it, but in a way to have an intuitive understanding of quantum information, so they can avoid irrational exuberance, or they'll be able to see what's likely to be true rather than to be either intimidated or over-enthusiastic and not know, to develop some common sense or good taste about quantum things. Now, speaking of not my job or not our day job, I'm going to say something a little depressing. And that is, people around here often ask, is quantum computing or is quantum the next big thing? And it's not any of our day jobs, but technologists often forget that the next big thing is often not technological. In 1929, it was a financial collapse. In 1939, it was a war. Maybe some of you are too young to have been alive during that war. In 2019, it was a pandemic, and maybe this year it's a period of geopolitical strife and economic fragmentation and so on. Maybe so bad that it kind of eclipses the world that we're used to, where we walk around with these miraculous machines in our pocket, which maybe the world will be too disorganized to make them anymore. And we have to go through a period where we look back on the glory days of technology for a few years before we get our act together again. But that's not anybody's day job, but I guess it's in the back of everybody's mind to try to preserve what we have or maybe improve it. Now I'm going to go on and try to explain, to make quantum information, quantum computation, seem more natural, intuitive and easy to understand for somebody who's had, I'm going to try to explain it in a way that doesn't need anything more than high school algebra. But fundamentally, like other parts of mathematics, information science originated in abstractions from everyday experience, especially Turing's abstraction, a universal hardware-independent notion of computing, which has pretty much been absorbed into common sense. And even more revolutionary was Shannon's meaning-independent notion of communication. Now, like, what could be more obviously crazy than that idea? But yet it turned to be very fruitful. So we're still in the middle of the information revolution, which sort of began around the time I was born and is still going at full steam. Now, it's one of the outstanding features of it is that even lay people are familiar with the content of Turing's 1935 paper. Was it 35 or 36? So around then. Essentially, they understand computational universality when they say, go into a computer store and say, well, do you have this app for my Mac? And they also understand the fundamentals of what Shannon discovered with in information correction and error correction and data compression. But chemists and physicists have long known that information doesn't behave in the way that's entirely described by the principles of Shannon and Turing. And this was the thing that was belatedly understood, began to be understood in the 1960s and 1970s. And I'm going to talk about that. But first I'm going to say, how do you explain this in an elevator or at a cocktail party? And when you start talking about vectors in Hilbert space, people get to glaze over and they don't want to listen to you anymore. So I find it helpful to say that everybody understands what ordinary information is, but quantum information is more like the information in a dream. And if you try to describe your dream, it changes your memory of it. And so eventually you forget the dream and you only remember what you said about it. And you can't prove to somebody what you dreamed. And you can lie about your dream without getting caught, unless you try to lie to your spouse about it. But unlike dreams, quantum information has well-known laws. And despite these differences, there are important similarities between classical and quantum information. And this was not noticed really because of the success of Turing and Shannon. That is, people were thinking of information as classical information, and quantum information is just a kind of unreliable kind of classical information, which you could deal with the tools that Shannon gave us for error correction. I'm going to get to that slide a little bit later. But the central principle of quantum mechanics is the superposition principle. And this is that as between any two reliably distinguishable states of a physical system, there are intermediate states that are not even in principle reliably distinguishable from either one. And that mathematically these the possible states of a physical system correspond to directions in space, not ordinarily three-dimensional space, but a space that has as many dimensions as the system's maximum number of reliably distinguishable states. In any direction is a possible state, but two states are reliably distinguishable if and only if their directions are perpendicular. Now, this tries to put it in mathematical terms that are understandable to high school algebra, but it's getting a little hard. Fortunately, you can get the gist of it by thinking about things that have only two reliably distinguishable states, and I'm going to illustrate the directions by the position of my arm. And the things that show this most clearly, and though they're often talked about as qubits now, but the most intuitively viewable form of qubits are polarized photons. So a photon can have a polarization that's in any direction, perpendicular direction of propagation, and it has some properties. That is, you can't measure the photon's polarization exactly if you just have one. You can't clone it, and you can use these polarized photons to carry information. So, for example, you can say, if I want to, where's that? Can you see even that? I don't even see that. Do you see that? Yeah. Okay. You can. This device will separate horizontal ones from vertical ones. But if you put in photons that are polarized in the intermediate direction, instead of being deviated by an intermediate amount, they behave randomly. So measuring photons along any other axis causes them to behave randomly. and forget their original polarization. And so this means that you can, if you know they're vertical or horizontal, you can use each photon to carry a bit. And if you know they're left diagonal and right diagonal, you can use each photon to carry a bit and then just rotate your measuring apparatus. But no measurement can distinguish all four kinds. And this is not a limitation of particular measuring apparatuses. This is a fundamental consequence of the superposition. And this gives rise to the possibility for, well, first I'm going to say that's a little this is something that puzzled Einstein a lot. How, if you prepare something identically, how come it behaves randomly? There must have been something about it when you prepared it that was different to cause it to behave differently. It's like if you go to a hospital full of sick people, some of them are going to die tomorrow and some of them aren't. But the ones who die were sicker already. But if you take a piece of radioactive material, the atoms that are going to decay tomorrow are not any sicker than ones that aren't going to decay tomorrow, and the photons that go into one beam are not any different from that goes to the other. Well, now, my colleague Bill Wooders from Williams College has a nice pedagogic analogy of how this quantum unpredictability. He says it's like the old-fashioned kind of school where the teacher is not, the students are not expected to talk to the teacher other than listening and learning. And the teacher asks questions. So the teacher says, are you vertical or horizontal? And the photon says, oh, I'm polarized at about 55 degrees. I believe I asked you a question. Are you vertical or horizontal? No, horizontal, sir. Did you ever have any other polarization? No, sir, I was always horizontal. So that's how they behave. Now I'm going to tell you why they behave that way. Now, going back to this early history, my college classmate, Stephen Wiesner, who died a couple of years ago, was a grad student at Columbia University, and he noticed, really, I think for the first time, that these quantum effects could do things that are qualitatively potentially useful and not describable under Shannon's theory. And that there's two that he described in 1968, combining two classical messages into a form from which the receiver could receive either one, but not both. And the other thing that he proposed was making banknotes that are physically impossible to counterfeit. And he submitted this paper to IEEE, IT, but he didn't pursue it much, and he went off and did other things, except he told me about it, and I thought it was really great, and I kept telling everybody else about it. And eventually, and also in 1970, he tried to improve this idea in his first paper. Well, I'll get into that a little bit later. But here's quantum money. It's a very simple idea. It's impractical currently because you want to keep 20 qubits of one of these four states, and the bank knows in which state it's recorded. And the point is that if the bank can check all those polarizations and find that they'd come out right, but a counterfeiter spoils some of them by trying to measure it. And this is what led to quantum key distribution. When I started talking about it with Gilles Brassard, and he was the first computer scientist who thought these ideas were as exciting as I did. And we worked with Wiesner a little bit on this, but Wiesner was not interested in cryptographic applications because he thought the whole field would get classified and it would be quite unpleasant. But that turned out it didn't happen. Anyway, now, I told you about this conference. Now, at that conference, Feynman urged people to rebuild Turing's theory of computation on quantum foundations. And this idea also occurred to David Deutsch at Oxford University, who was not at the conference. Here's a view of the conference. There's some of these people are, a a lot of them are still alive and continue to achieve other things. But this quantum key distribution is a Cold War kind of idea. The good guys trust each other and know who they are, and they don't trust their adversary, and there's more of them than their adversary. But nowadays, especially in the business world, the good guys don't trust each other, and you'd like a kind of cryptography that works where you have to deal with somebody who don't trust each other. And then the idea is you want the two guys to be able to negotiate. Suppose they want to, suppose these are two people who are considering getting married, and they don't want to tell everything about each other because it might spoil the deal. And they must cooperate. And so the normal way to do this is to go to a marriage broker and explain the situation, and the marriage broker then tells you whether to get married or not. But in the business world, they don't trust, no one trusts an trusted intermediary enough to do that. So what do? Well, this is the other invention that Wiesner found, combining two messages into a form that when you read it to get one, you spoil the chance of getting the other. Now, this idea was independently discovered and published, unlike Wiesner, because he hadn't published it yet. And it turned out to be an important cryptographic primitive that can allow this kind of discrete EET, discrete decision-making to be done without a trusted intermediary. It's very important. It was called oblivious transfer. And Wiesner found a quantum way of doing it. And then, even in his original paper, hinted that it was fundamentally insecure. That is, it's insecure against somebody with a very good quantum computer, or he didn't put it that way, very good quantum measuring apparatus. Insecure in principle, but secure in practice. And this was recently shown conversely, that if neither negotiating party can store quantum information, techniques related to this multiplex provide a way of achieving provably secure two-party negotiation. Of course, the most fascinating thing about quantum information is entanglement. And this is the thing that creates the most confusion and misunderstanding, especially beginning with Einstein, who didn't like quantum mechanics. And he famously called, well, his two famous things that he said about quantum mechanics that he didn't like was that he didn't like the idea that God played dice by allowing identically prepared particles to behave differently. And he also didn't like spooky action at a distance, which is what entanglement appeared to be. There are various approaches to that, or called interpretations of quantum mechanics, or the shut up and calculate interpretation. But I'll just say about where it comes from, and a kind of way of making it seem comfortable and not unreasonable. And if Einstein were alive, he would probably get used to this idea now and would regret that he said either of those two things. But we don't know, because it didn't happen in our branch of the wave function. Oh, excuse me. Well, anyway, so any processing of quantum data can be done. This is a similarity to classical information processing that wasn't really appreciated. Suppose you have these input lines, these wires. I call them wires. Can anybody? Yeah, there. And just in a classical computer, they go through, either they just go straight through, or they get operated on by gates, and the gates only need to work on them 1 and 2 at a time. And here's one of the most important gates. It's called the controlled NOT gate. And that is, if we call a vertical photon a 1 and a horizontal photon a 0, if the control photon, I can hardly see that damn thing. Anyway, if the control photon is a 1, the other one is rotated 90 degrees. If it's a 0, it's left the same. And if you give it a superposition of inputs, it gives a superposition of outputs. Because it's a quantum device, it follows the superposition principle. And that means you get a superposition. If you give it this diagonal photon coming in, and you start with the horizontal one on the bottom, you get a superposition between both horizontal and both vertical, which is an entangled state. And this entangled state behaves in ways that can't be explained by supposing that each photon has a polarization of its own. And if you do the math, which is just very elementary high school math, this turns out to be superposition to both vertical and both horizontal, the same as superposition to both left diagonal and both right diagonal, and is not equal to them, both of them being diagonal. So it can be said, if you want to say it at a cocktail party, a state of sameness of polarization, even though neither one has a polarization. So the generalization in going from the sheer theory of Shannon and Turing to the theory of quantum information processing, which we have now, is not only potentially more useful, but is much more beautiful and elegant than the old theory, in the same way that the theory of complex numbers is more elegant and beautiful and encompasses the whole theory of ordinary real numbers. Anyway, a classical bit is just a quantum bit which happens to be in one of two standard arbitrarily chosen states, which we call 0 and 1. Classical wire is a quantum channel that conducts those faithfully but randomizes superposition. And it randomizes them for a reason, because it interacts with an environment. And so when we pass a classical channel is a quantum channel with an eavesdropper, and a classical computer is a quantum computer handicapped by eavesdroppers on all its wires. So people shouldn't be talking about why is there quantum speed up. They should ask why there is classical slowdown. In other words, why are there some calculations which, if somebody is looking over your back while you're doing them, you can't do them as well? That's the question we should be asking. Now, this can be explained by a property that I think I was responsible for this name. It's called a phenomenon called the monogamy of entanglement. And this is certainly an analogy, but a fruitful one to human relations. If A and B are maximally entangled with each other, they can't be entangled with anyone else. And if one member of the entangled pair tries to share the entanglement with a third party, the pairwise relation is reduced to mere correlated randomness. Or as they say, 2 is a couple and 3 is a crowd. So let's take Alice and Bob here, who have become entangled by having this controlled knot interaction. And this means that they are correlated along any axis of measurement. If you measure Alice, you'll find out what Bob would respond to the same measurement. You'll know the state of Bob. And suppose that Bob likes this, and he says, well, I'm going to get entangled with somebody else here, so we do that. And then at this point, we end up with this kind of situation where Bob shares only correlated classical randomness with Alice and also with Judy. And if one of Bob's girlfriends leaves, he will find his relationship to the other reduced to mere correlated randomness. But if they both stick around, he ends up perfectly correlated, perfectly entangled, not with either one, but with the now non-trivial relationship between them, an appropriate punishment, which was explored by Colette in this book, which came out right around the time of quantum mechanics, although I believe she was unfamiliar with it. So where does this quantum randomness come from? So I kind of lied to you about this when I said these photons go into that crystal and they randomly go into the top path and become horizontal, or the bottom path and become vertical. Well, what really happens is that they go into a superposition of being horizontal in the top path and vertical in the bottom path. And only when you measure them and detect that the photon is in the top path, then it will also turn out to be vertical. Well, suppose you don't measure them. In fact, if no one observes their behavior, Bohr would say you can't call it behavior, or as our late colleague in teleportation said, this is Asher Perez, he said, unperformed experiments have no outcomes. Well, anyway, so if you put this, before you combine these two beams, if you put a half wave plate there, which rotates vertical photons to horizontal and vice versa, the two beams will go back together and they'll recover the original polarization. Now, putting that in terms of Bill Wooter's analogy, it's the public embarrassment of the pupil in front of his whole class that makes him forget his original polarization. So if he could undo that awkward answer to the professor's question, and all of the other students and any air molecules that might have heard his answer could forget what he said, he would get his polarization back. So entanglement is ubiquitous. Almost every interaction between two systems causes entanglement, and yet it wasn't discovered until the 20th century. And the reason it wasn't discovered is because of monogamy. Most systems in nature, other than little ones like photons, interact so strongly with their environment that they become entangled with it almost immediately. And this destroys any previous entanglement that might have existed between parts of the system and changes it to mere correlated randomness. Well, of course, everybody is excited about building a quantum computer, mainly because it could speed up some computations, and there may be other ones that we don't know that it could help, and there's therefore a tremendous amount of research going on. This is the most famous type of computation accelerated by a quantum computer. This is a showing that using Shor's algorithm. This number over here could be factored in as a product of these two numbers. Now, it's a really hard computation to do in this direction, but if you had a quiet weekend, you could multiply this number by that number. So you multiply the 3 by the 7, and you get 21, and that's where this 1 from over here comes from. And you carry the 2, and nobody's looking over your shoulder. You can do it without a computer, but with a computer, it's very hard on a classical computer, but easy for a quantum computer. So aside from their applications to communication and computation, and really, the word, we don't use it much in English, but it's a better word, informatics, the science of communication and computation together. Quantum information science has already improved precision measurement and timekeeping. And I would say most excitingly, it has provided tantalizing hints about some of the deepest mysteries in physics, such as the black hole information problem and quantum gravity and the origin of space-time. And here is a speech given by John Preskill, who knows far more about those things than I do. But I want to make a remark again about basic science and the importance of it. Most people are interested in what science can do to solve what they consider their most pressing problems. But scientific progress is mostly incremental. Breakthroughs are overrated. And the most important applications of a scientific discovery are hardly ever the ones that people think of first. And in fact, it's likely to be even maybe there'll be 100 years after the thing was discovered. Think about radio and the cumbersome equipment that was used to send telegraph messages across the Pacific. It was obviously a great and important idea in the Atlantic Oceans by Marconi in the early 20th century. But Marconi would not have thought that I have a thing in my pocket that sends radio messages to my wristwatch. And so when anybody tries to telephone me, I have to figure out whether I'm going to answer my watch or my phone. Anyway, so this is, I'm preaching to the choir, or at least some of you out there are the choir. It's most important to keep steadily supporting science, and mostly don't worry about the applications of it. And even in applied sciences, ideas go through ups and downs on a scale that's sometimes longer than a human lifetime. For example, around the time I was in kindergarten, people were talking about computers that recently discovered. They called them electronic brains. And they said they'll soon solve problems such as language translation and will revolutionize the world. Of course, they did revolutionize the world, but they didn't solve the problem of language translation until around the time that, that I met my wife, and we spoke different languages, but We were sitting there talking to each other through Google Translate. Anyway, but that was about 60 years later. More than that, 70 years later, something like that, yes. Anyway, artificial intelligence is very hot today, but it went through a long dormancy. So this is just that. So I would say it's important to work on these toy problems, and I think, except for people who have a irrational conviction that quantum computers will never work, it's not very important to just show that you've done something that a classical computer can't simulate, if it's not an important, useful thing. The important thing is just to keep improving the quantum computers until they can do some of these things that are worthwhile. And anyway, they may never be the biggest part of the information revolution, but they're such an important part of the way things are that everybody should understand them. In fact, I say, where we go? So wait, was one. Yeah, it's like the roundness of the Earth, or basic understanding of what black holes are. Every educated person should have that, understand the gist of quantum information. And if, just to be a well-educated person, I think Einstein probably stood in the way. Most people think that quantum mechanics is too hard to understand. It's much worse than rocket science, but that's not true. And if you want to get a longer version of my talk, there it is up there. And if you want to find out more about this very unusual person, Stephen Wiesner, who had some of these ideas so long ago, you can look here. Okay, I'm done now, I think. I'll take any questions. How does this work? Where did my share bar go? Yes.
All right, thank you very much for really interesting talk and for your insight. Maybe we could have like one quick question from audience. Yes, please go ahead.
Thanks, great talk. I'm going to ask a pretty obscure history question. So you talked about Deutsch and yourself and a couple of the others in the early 1980s in the work you were doing. What about Paul Benioff's work on quantum Turing machines? How would you place that in the...
Oh, yeah, I knew him well. He said, of course, that we believe the universe is fundamentally quantum mechanical. And so therefore, the idea that the universe can perform a computation has not been made rigorously demonstrated unless we can show a quantum system can perform computation. So he tried to show that a quantum system describable by a Hamiltonian could perform classical computations. And that was his big result. He remained interested in the field. I think he may still be alive, but that was what his approach to it was.
Thanks.
Right. I'm pretty sure many people has more questions, but I think it'd be better if we take the questions to the break. Let's thank Charles Bennett again. Thank you very much.